We're going to introduce two topics here, resonance and hybridization. The first one we'll do is resonance. First of all, the word resonance, you may or may not recognize this word, but basically resonance means something that kind of, vibrates, or something that really rings, that. And in terms of sound, things can resonate throughout a room, but also, maybe in terms of like ideas or concepts, someone brings this idea, that, maybe a hot dog is a sandwich, and that resonates with you. You like that. That sounds good. To a certain degree, this also kind of works. In the process of sketching a Lewis structure for ozone, you'll actually encounter the structure once all the electrons have been assigned. So again, in the process, I'm going to go and skip ahead a little bit. At some point, you'll encounter this guy. Okay, and then you'll kind of have to make a decision. Because if you remember in this step of the process, once you've assigned all the electrons, you got to see that the octet rule is satisfied for everything. This guy in the middle, this one is not satisfied, right? That only has 6 when it still needs 8. So to finish the sketch, what are you going to do? You're going to have to draw a lone pair in from the outer atom to make a double bond. Remember this? So then you look over here, right? You have kind of two options here. This is not as pretty, so let me recreate that one. So then you have two options here. You can either take a lone pair from the left one, bring it to the middle, or you can take it from the right one and bring it to the middle. Which one do you choose? It turns out either one's going to result in identical Lewis structures. All right, so let's see what that would look like. If I decided to pull from the left one, it would look like this, right? You'd have this here, that double bond formed there, and then now you have your octet rule satisfied with your central atom. Alternatively, I can bring it in from the right side, right? So I can bring it in, again, as an alternative to say, all right, I want to pull my lone pair from one of the outer atoms to the right instead of to the left. And end up with something that looks like this. These are identical pretty much, right? But they're sort of like, in this case, mirror images of each other, but otherwise, they're connected the same way. Everything is basically just sort of moved around a little bit. So if I know I have these identical structures, well, which one is better than the other? Not really. There's none of them. Neither of these two is necessarily more right than the others. So these two structures, we call them resonance structures. Resonance structures. The reality is that this ozone, right, the actual molecule, it's actually kind of an average of those two structures. Now, again, we say this because this is kind of something we can determine experimentally. With chemical analysis, there's not really like a single double bond. Like there's no single bond right there, and then you don't have an actual separate, distinct double bond. That's, again, on the drawings, we might see that, but that's because we as humans try to represent reality on paper sometimes, and they don't always connect and go one for one. In this case, it turns out it has two kind of like 1.5 bonds. So it's kind of like they sort of blend these two together. If you don't know what I mean, basically this kind of loose analogy is where green is like a blend of blue and yellow, right? To mix those two individual parts, green is there. You don't really see individual aspects of blue. You don't see individual aspects of yellow. You just see what the result is of the blend. In comparison, right, the resonance structures with ozone, right, this is the one that we used on the left. This is the one that we drew on the right. And again, the actual molecule is kind of a blend of the two. This is like our green, where you don't really see this necessarily. You don't see the left one or the right one individually. It's kind of the blend of the two. Unfortunately, it's difficult for us to actually write on paper, right? It does exist. It's the thing in reality out there in the world, in our atmosphere and everything. But for us to draw on paper, it's a little more complicated. So really, we just kind of assume that both of them exist, and they kind of go back and forth. They sort of exist at the same time. To kind of help indicate that, we represent the relationship between these resonance structures. We use a double-sided arrow that we draw between each of the resonance structures. So if I go back up here, right, these are my resonance structures. This is one resonance structure. Here's the other one. The double-sided arrow I'm talking about looks like this. Right, so guys go back and forth. So in that way that things resonate, right? They kind of vibrate and go back and forth. This is kind of the same idea. It's like, really the Lewis structure is some blend of these two that go back and forth. If you can imagine it, this double bond sort of swapping back and forth to go between this structure and this structure. Anywho, in practice, let's see what this looks like. So we're going to draw the resonance structure of our friend carbonate. Carbonate is going to have a couple of valence electrons. Turns out there's 24 of them. So let's go ahead and put this in action. Carbon in the middle, oxygen's on the outside because those are more electronegative. Go ahead and draw in all of the single bonds, and then go and start assigning a bunch of electrons to our lone pairs, or as lone pairs, to our outer atoms. So at this point, we reach this step. Once again, you're kind of realizing, right? all three of the oxygens more or less look identical. Except now we're not done because the carbon in the middle is not quite satisfied with this octet rule. So what do we have to do here? We have to bring in a lone pair from the outside. Which one do we bring a lone pair from? Well, they're all kind of the same, so it doesn't really matter. For the sake of just starting, we'll do it at the top. So I'm going to go ahead and redraw this one so that you have a lone pair there that we drew and pulled in from there, and then bring it to the middle. And then to finish this one off, right, this structure has a charge of 2-, and we put square brackets around it. But like we said, if I'm asking you to draw the resonance structures, if it's asking you to draw the resonance structures, go ahead and draw the rest of them in. So then we draw this double-sided arrow business, and then we do this guy to where we do C. At this point, we know that we ended up with something that looks like this before, right? This was our structure before I started double bonding it. Right, 2-. But, right, at this point, we can choose now to use another outer atom to move our lone pair in from. So let's do it from down here. Keep erasing too much. Boom, just like that. So it looks like the double bond just kind of moved from the top one now to the bottom left one. And then as you can imagine, right, this last resonance structure, which basically again is identical, but the only difference here is the location of that double bond. So now we slap it on this last one because the same process would occur. You'd end up with that kind of intermediate one where you have to decide which lone pair to bring in, and then you finally move it to the last one. This next one right here, draw the resonance structures for our friend nitrite. So nitrite, real quick, this one has a total of 18 valence electrons. Right? So then we go and start assigning it. We have nitrogen in the middle because it is less electronegative than oxygen. I'm going to kind of race ahead a little bit, sort of assuming you can draw the Lewis structures according to the process. You end up with something that looks like this, and then you kind of have to decide, right? There's just only one. You have to decide where you're going to pull the lone pair from. So again, let's do it first on the left side just because it's there, double bond. And then we do it again over here, and you can probably race ahead if you sort of know what it's going to look like as a result. But if you need to take the time anyway to draw it out individually. Excuse me, drew too much there. That's fine too. There you go. That's basically how it works. All right. I will let you try to draw this last one out. Draw the Lewis structure for hydrocyanic acid, HCN. Does this molecule have resonance? And you can figure that out yourself. If it does, go ahead and draw it. If not, you can just leave it as is. That's resonance. So let's go ahead and move on to the next one, hybridization. This one's a little bit more complicated. And I just want to preface this by saying that, I'm going to introduce to some background here just to give you kind of an idea of what's going on. But remember, at the end of the day, that bottom, there's a little cheat sheet here. At least what looks like a cheat sheet. That's probably the biggest takeaway for this section. Hybridization. Now, hybridization, you may recognize the word hybrid, hybridizing. So hybrids are basically kind of a mix of two different things. In this case, what are we mixing? Let's find out. Atoms bond to each other because their orbitals overlap. Remember, these are those regions where electrons are located. Orbitals of one atom and orbitals of another atom will overlap to form a bond. However, this fact alone, just that overlapping, doesn't explain pretty much the shape of any of our molecules. Right? So again, we're talking about atoms that bond together. They make molecules. Why are then the shapes the way they are? Let's use this example to kind of illustrate that idea. Let's go ahead and take one carbon atom and 4 hydrogen atoms to eventually make our friend methane, CH4. Our focus here is going to be on the central atom, carbon. All right. Now, again, I know hydrogen is still important, but that's not the main idea that we're trying to show here. So we're going to take a look at these two diagrams on the left to illustrate that point. First of all, this bond is going to end up requiring carbons S, actually let's do 2s and 2p orbitals. Now, just kind of keeping track of this, how many 2s orbitals are there in carbon? There's only one of them, right? How many 2p orbitals are there in carbon? There's going to be 3 of them. So then, right, if you look at this, before the bonding, these orbitals have angles of 90 degrees in relation to each other. So let's take a look at this guy. This is our friend carbon here, right? So this is carbon, just the atom that's unbonded. What you notice here is kind of these like little dumbbell shapes, right? The ones that we described from before. These are your p orbitals, right? These p orbitals, what you notice about their arrangement is that they're kind of, 90 degrees in relation to each other. So you can imagine that's 90 degrees there, that's 90 degrees between these two, right? It's kind of 90 degrees right here between these, right? These blue lines act as axes. Kind of looks make a little smiley face there. Whatever the case, those are 90 degrees in relation to each other. But what do you know about carbon after it's being bonded with hydrogen? So carbon being bonded with hydrogen, the bond angles now have a bond angle of 109.5 degrees. Right? That's because, again, it's tetrahedral. It has a known bond angle of 109.5. So if you look at this guy right here, right, this CH bond, so this bond and this bond, these have an angle of 109.5 degrees. And this is, again, our carbon that we're focusing on the middle that's being bonded, right? It's already bonded now to hydrogen. You see the hydrogen is now appearing here that weren't there before. That is a terrible carbon. Let's try that again. So what happens now, right? How do we get from here to here? What exactly happened for it to go from 90 degrees in your original unbonded one, and then all of a sudden becomes 109.5? Did things just kind of get pushed around some? Well, it's not quite as simple as that. It turns out there's a little bit more involved, and we're going to use the combination of this diagram here on the right and, again, this little description. So to address this, why exactly it does do that, chemists use the concept of, that's not what I'm looking for, hybridization. Right, hybridization. So it's basically taking something and hybridizing it. You'll hear various combinations of that word: hybridization, hybridizing in various forms. But basically what this means is that we're mixing two or more atomic orbitals, right? So orbitals of just a single atom, to produce new hybrid orbitals. So atomic orbitals hybridize into hybrid orbitals. So what does that mean? In carbon, the 2s and 2p orbitals are hybridized. Let's try that again. Hybridized, right? Like we said, we're taking that hybridization and making that into a verb form to make 4 identical hybrid, coming around here, orbitals, which allow carbon to form 4 identical bonds with those hydrogen atoms. All right. So, by the way, it's kind of potentially confusing, right? Hybridization and hydrogen, like the high sound at first, you're probably catching on to that. They're not related at all. It just kind of happens to have that same initial sound. The point is, looking at this diagram here, right? What do you notice? Well, again, this is carbon's orbitals. You have the 1s, 2s, and 2p. You have the 2s got some electrons in it. The 2p's got some electrons in it. And basically, they're going to take these and they're going to put them in a blender and they're going to crunch them up, basically. And then they're going to reshape them into 4 identical hybrid orbitals. Now, notice the label here, right? We had 2s, we had 2p. Now it just becomes this brand new thing called sp3, right? The s and the p kind of stick around, but then you got this little 3 in front, right? We're going to talk about this some more in a bit, but essentially, that's what's happening. So you have the individual atomic orbitals here. You hybridize it to make 4 hybrid orbitals. All right, now, again, I'm not going to ask you guys to necessarily draw these diagrams. I'm mostly just recognizing that the language is here. We take some orbitals, we hybridize them into hybrid orbitals. Here's a cheat sheet. Hybridization can be assessed on the central atom. Right? That's basically our focus here. So as it turns out in our previous example with carbon, right, we had C. That's our central atom for that compound. So one, you're always going to draw the Lewis structure, always and forever. Or sometimes it'll be provided for you. That'd be nice. And what you're going to do is you're going to count the total number of electron domains. All right, if you remember that, right? Electron domains are basically areas of where electrons are. They can be bonding domains and they can be lone pairs. But again, focused around the central atom. Then you basically match that number with this chart below. All right, so for example, just a minute ago, we did CH4, right? I'm going to use this as an example. We have CH4, it has 1, 2, 3, 4 bonding domains, or the electron domains, period. And so if you look right here, right, if we have 4 electron domains, oh, looks like I kind of actually just caught a typo here, so let's scratch on a lamp. Let's try this. Let's do 2, 3, 4, 5, 6. So taking a look at this one more time. All right, so methane, you have 1, 2, 3, 4 electron domains. I'm going to check this chart, see that I have 4 electron domains on that column. The corresponding hybridization will be sp3. So like we said a minute ago, right, the carbon's orbitals, the hybrid orbitals anyway on carbon now, will be sp3 once it's bonded. Let's take a look at the next one. The sulfur tetrafluoride, SF4. This Lewis structure has been drawn out for you. So let's count it out. You have 1, 2, 3, 4, and then 5 electron domains, right? That's a lone pair that represents an electron domain, not individual electron domains as a pair. So then you have 5 that you want to check up here. Looking at this chart, 5 electron domains. That's going to correspond to sp3d. So the hybridization is going to be sp3d. Okay, that basically runs through it. See if you can do the next two here. So again, like we said in the process, make sure you draw the Lewis structure out and go ahead and match up the hybridization based on the number of electron domains and then list out the answer there. All right, that'll do it.